As in two-dimension coordinate geometry, here as well a line in space will be uniquely defined if you know a point and if you know a direction along which the line is defined, or if you know 2 points through which the line is passing. Now, in two dimension the direction was given or decided by what we called as the slope, which also depended on the angle which the line made with the horizontal axis. In the space, we replace that concept by direction cosines, and therefore, a vector comes in quite handy to understand the direction of a line. Today, we will be talking about the forms of line depending on what the information given is. So, a line is uniquely determined if it passes through a given point and has given direction, or it passes through 2 points. So, starting with our first possibility, to find equation of a line which passes through the point A with given coordinates, and also in dual language, as we said, we will be talking about the concepts with position vector, vector A. And the second thing that we are given is a vector to which the line is parallel. So, that vector is known to us. Let us take that as A I cap plus B j cap plus C k cap. Now, what we are looking at is a locus of any point on this line. So, suppose P with x, y, z be the any point on that line, and let its position vector be the vector r. So, what you are looking at as in this figure is a line passing through A and P and a vector along which the line is defined. So, if I look at this position of the point A and P, then the vector AP is collinear with the vector B, and vector algebra taught you that if I have the vector AP and B collinear, then one is scalar multiple of other. So, vector AP becomes lambda times vector B. Vector AP is nothing but position vector of the point P minus position vector of point A. So, that gives me an expression as r minus A equal to lambda times vector B. That gives us the vector equation of straight line passing through point A and parallel to the direction B, given as vector r is equal to vector A plus lambda times vector B. Again, it is essential for us to translate this information in Cartesians. So, if I replace vector r, vector A, vector B in terms of their components, then I get an equation of the kind x I cap plus y j cap plus z k cap equal to x1 I cap plus y1 j cap plus z1 k cap plus lambda times the vector B getting replaced by A I cap plus B j cap plus C k cap. If I equate the I cap, j cap and k cap coefficients, which are nothing but the components of the vector in the 3 directions on the 2 sides, I get x is equal to x1 plus a lambda, y is equal to y1 plus b lambda, z is equal to z1 plus c lambda. And these equations are referred to as the parametric equations of the line in space. If I remove lambda from these expressions, I get an equation as x minus x1 by a equal to y minus y1 by b equal to z minus z1 by c. This is what we are looking at as the Cartesian equation of the line. Also note that a, b, c, the denominators in this form are the direction ratios of the line. These were the direction ratios of the vector to which the line was parallel, and they are what are defined and used as direction ratios of the line. And if L M N are direction cosines of the line, then the line's equation in Cartesian will look like x minus x1 by L equal to y minus y1 by m equal to z minus z1 by n. Let us try to consolidate what we have talked about in this little section. If I have the equation of a line known in vector or in Cartesian form, there are certain information that are immediately available. What would they be? If I have equation as x minus x1 by a, y minus y1 by b and z minus z1 by c, or vector r equal to vector a plus lambda times vector b, we immediately know a point through which the line passes, that is x1, y1, z1, and direction ratios of line are a, b, c. In addition to all of this, what is most important is that we also know coordinates of any point on this line. That would be x1 plus a lambda, y1 plus b lambda and z1 plus c lambda. For a specific condition, this lambda can be calculated, and that will give you a specific point which would satisfy the given condition. Also, in language of vectors, it would mean that I know the position vector of any point on this line as this. So, this is an information that is always available with us. The second form of the line is defined if I know two points through which the line passes. So, let us take a look at what that equation will look like. So, suppose A x1 y1 z1 and B x2 y2 z2 be 2 points on the line with position vectors vector A and vector B given to us. P be any point on the line with position vector r. And again, if you look at the figure, it tells you exactly what we are going to do. The vector AB and the vector AP are collinear, and therefore, one must be scalar multiple of other. So, vector AP is lambda times vector AB. Using the position vector of each of these points, I get an equation r minus A equal to lambda times vector B minus vector A, and that gives us the vector equation of line passing through two given points as r is equal to vector A plus lambda times vector B minus vector A. If I convert this into Cartesian by eliminating lambda, I would get x minus x1 by x2 minus x1 is equal to y minus y1 by y2 minus y1 equal to z minus z1 by z2 minus z1. Something which is very familiar, you did almost the same thing in 2 dimension as well, finding equation of a line passing through 2 points. So, if you do not have the z minus z1 component, that is exactly what we had earlier. Now, with these two equations, we are ready to look at some applications as well. But what happens if I am interested in talking about two lines in comparison to each other? Can I talk about the angle between the two lines? Well, if two lines are defined along two different vectors, say b1 and b2, then the angle between the two lines will be same as the angle between those two vectors, and you, I think, should be ready to answer that. So, let us take a look at the result that we have here. So, if theta is the acute angle between the two lines, then cos theta is same as the absolute value of b1 dot b2 by magnitude of b1 vector into magnitude of b2 vector. In Cartesian, we can always use the direction ratios of the vectors, and I get the result as cos theta is equal to absolute value of a1 a2 plus b1 b2 plus c1 c2 divided by the magnitude of b1, which is under root of a1 square plus b1 square plus c1 square into under root of a2 square plus b2 square plus c2 square. This also enables us to talk about what happens if the lines are perpendicular. If lines are perpendicular, then theta must be 90 degree, cos theta therefore should be 0. That gives you the condition a1 a2 plus b1 b2 plus c1 c2 must be 0. If two lines are parallel, then angle must be 0, and therefore, the direction cosines or direction numbers must be proportional of those two vectors, and in this case therefore A1 by A2 must be equal to B1 by B2 equal to C1 by C2. These two results will be in use as we go along learning more on lines. Let's take a question which consolidates all that you have learned today. The question says that find the foot of perpendicular from the point whose position vector is I cap plus 2j cap minus 3k cap to the line r equal to minus I cap plus 3j cap plus t times 2I cap minus 2j cap minus k cap. We also have to find the length of the perpendicular. So, when you look at this situation, if I take a point A from where the perpendicular is drawn, then I need to find the coordinates or the position vector of the point P. Also, if I look at the point P, that is any point on the line, so its coordinates are known to us by using the equation of the line as minus 1 plus 2t times I cap plus 3 minus 2t j cap minus t k cap. So, you look at the equation of the line and use that to find the coordinates of any point on that line. Let us find the direction ratios of the vector AP. So, I know that the vector AP is position vector of point P minus position vector of point A. So, I have the vector AP known. We have the vector B to which the line is parallel. So, if AP is perpendicular to the line, then L is also, the vector AP is also perpendicular to the vector B. So, AP dot vector B must be 0. So, find the dot product between these two vectors. In this case, that gives us t equal to 1. Once I have the value of t, what are we going to do? Find the point P. So, put value of t equal to 1 in the position vector of the point P, and you get the point P as I cap plus j cap minus k cap. What else we need is the distance. So, if I use the value of t, then I know what the vector AP is equal to, and therefore, the distance of the point from the line will be same as the magnitude of this vector, which turns out to be simply square root of 5. And therefore, the position vector of foot of perpendicular is I cap plus j cap minus k cap, and the perpendicular distance of the point from line is root 5 units. So, what we have discussed today is the forms of the lines, how to discuss angle between the two lines, and also how to use the given condition to find a specific point using the understanding of a general point on the line. All of these are important, very significant results, and we will be using them in our future lessons as well. So, let us hope you are there to watch and understand and learn from our next few chapters as well. See you again.